Welcome to the second part of the deep learning day. And this second part is going to focus more on, given all the tools that you have seen this morning, how do we build systems around them and the type of things that you can do. And in this particular hour, well, 45 minutes, so that I will be talking, I'm going to focus on agents, which is a kind of ill-defined concept. So, at the end of these 45 minutes, you will be equally confused. Don't worry about that. And I wanted to just give you a couple of examples of agents that I find interesting. So the first thing is that when some of us started working on the field, in particular when I started, around the decade of the year 2000 and so on, it was what we call the benchmark golden era. We have images, for instance, if you were building a computer vision system, we had databases where every single object was annotated. We knew exactly what the ground truth was. We knew what had to be done. There were data sets with lots of images, all annotated according to some criteria. And that allowed us to evaluate algorithms. And you could rank them, which one was better, which one was worse. Things were very easy. You could take a picture, like this one here, run the state-of-the-art computer vision algorithm at the time, ask what is the content of this picture, and the output was this. And you knew this was wrong. Everybody will agree with that. And -1 point for this detector, and everything was very, very clear. We are not living in that time anymore. We have models that can do all kinds of very sophisticated things, and it is really hard to evaluate how good they are. In fact, it's an open area of research to try to find ways of evaluating these systems to tell which one is better than which one. And as Philip was showing this morning, there's been a revolution on the speed of how advances are happening. From the 60s to the year 2000, basically we went from very simple neural networks to the first face detection systems that actually kind of worked. But in the last decade, we had like an acceleration of all kinds of systems converging to the large language models that we have today. And they can do all kinds of things. You can use ChatGPT for many, many things that are really interesting. Here is an example of asking ChatGPT to solve a high school math problem where you say, well, there is a treasure hunter found a chest filled with gems. There are 175 diamonds, and so on and so on. How many gems are in the chest? And ChatGPT gives you just an answer with beautiful reasoning, explaining all the different equations that you need to think about, where the unknowns are, and at the end it tells you the total number of gems are 225, which is wrong, but who cares? It's so beautifully written. It's better written than the question itself. It's just amazing what the systems can do. So the thing that is happening now that everybody is very excited about, at least for the last 2 years now, is AI agents. And I think this will remain a very hot topic for the future. And by the future, I mean the next 6 months, more or less. So what is that has enabled agents to appear? I think there are a number of different aspects that build what is the infrastructure of an agent. One is the fact that these models, like ChatGPT and so on, they are not unimodal anymore. They are not models that only deal with language. You can actually mix different modalities. For instance, you can input text and a picture, like in this case, and you can ask ChatGPT, this is GPT-V, what happened here? And this is a neural network that will take everything as input, images and text. Everything gets translated into tokens. At the end, everything is kind of the same, and it will just generate an answer, and this is the answer that it gave, which is a pretty good description of what makes this picture interesting. And it could have been describing what is happening on the background of the picture, but no. It did focus on the object that is actually interesting for us humans. When you look at this picture, the interesting thing is this car in the swimming pool, and that's what ChatGPT is talking about. There is this, I was showing also this example where you have this high school math problem, and ChatGPT got it wrong. But there are also a number of other things that people have been discovering that you can do with these models to make them better. Besides just training them more and making them bigger, there are other things that you can do. So for instance, one thing that 2 students here at MIT did was to, one thing that happens every time that you ask ChatGPT the same question, it will always give just different answers because it's just sampling from the probability distribution of different words. and it will generate something different. It might actually mean the same thing, but it will have different wording. In this particular case, if you ask to solve this math problem to ChatGPT, the first time, it gives you the answer that I showed you before, which was wrong. But the second time, with a different instance, the same model, it just gives something different, and it actually happens to be right in this case. You, as a user, you don't know which one is wrong or which one is right. You just know that there are two different answers. So one thing that you can do is to have these two agents, these two different language models, debate between themselves. So you can now take the second answer and just copy-paste that text into the dialog window of the first LLM and tell the LLM, a different version of you say something different. Here it is, and just copy-paste the answer. What do you think now? So if you do that, it changes its answer, it revises the answer, and in this case, agrees that the right one is the one given by the second one. Because you don't know which one is right, you just do the same thing with the second one, with the second LLM. You do the same thing, you copy-paste the answer given by the first one, and in this case, it just still sticks to its answer. So what they found is that when you have these interactions between agents, they converge more likely than not to the correct answer. So you can do this with all kinds of things. Here is trying to answer a question about some mathematical calculation. And if you ask this to two different agents, both get it wrong the first time. But once you copy the answer to one between themselves, they realize that there are other possible answers, and they just start keep revising their answers. So in the second round, the second one got it right, and the first one still got it wrong. You can do this again, and eventually both of them converge to the right answer. This is not always the case, as you can imagine. This is not always going to be working. But what they showed is that the more agents you put together, the more rounds there are, performance seems to be improving. And we haven't really seen a plateau here. It just keeps doing better and better. But of course, this is going to plateau. There is so much more you can do. But this is an example of where creating a society where you have a few different language models interacting with each other, you can build something that works better than each of them in isolation. We have seen also that you can use these language models to write code. And this is another very important piece that will allow systems to become agents, where you can give an instruction, you give a specification of something you want to do, and the LLM, it outputs code that, if you run it, supposedly it will actually do what you ask it to. So this coding capability is actually a very powerful way of then having this LLM to be able to actually interact with the world. Because once you write code, you can execute that code, and that code can perform operations in the physical world. So, these language models are very powerful. For instance, in coding, they are amazing. You can go use the ChatGPT, you ask it to write a MATLAB script that draws a bouncing ball inside a square, which is a very typical problem that you do when you are trying to learn coding, and this is what the output is supposed to be. It's just a ball bouncing inside a square. If you ask this, ChatGPT gives you a script that it looks pretty good with comments and everything, and if you take this and copy-paste it on the MATLAB window and you run it, indeed, this is the result. It works really well. So, one can think these language models are amazing, how they do this. Well, another very important thing not to forget about is that these models are trained with a lot of data. And sometimes the power of these models is not really the model itself, it's the data. So, in fact, if you go to Google and you ask for examples of MATLAB scripts of bouncing balls inside the squares, you get tons of different examples, and ChatGPT has learned from all of those. So the web contains a lot of information. These models have been trained with an amount of data that is just so much bigger than the amount of data that you have seen in your life that it's just hard for us to grasp our heads around how much data they have seen. These models have all kinds of really interesting properties. For instance, the generative models that Camille was describing, they show some interesting compositional capabilities. For instance, if you ask an image generative model like DALL-E to draw an image of a cup of coffee, it draws a picture that looks like a cup of coffee, very realistic. If you ask a picture of a cat, it generates a picture that looks like a cat. And if you ask for a cup of cat, it gives you this, which is quite amazing. No? You think, oh, wow, it really understood these visual concepts, and it understood what will be a coherent composition between these two concepts, despite that this is something like you cannot have seen this in the real world. Well, you think you cannot see this in the real world, because if you go to Google and you query for a cup of cat, then you realize that people are putting cats inside of cups very often and taking pictures of them and putting them on the web. So sometimes some of the capabilities that we see of these models, they are really a reflection of how rich is the training data that has been used to train them. That doesn't mean that they don't exhibit some of these compositional capabilities that go beyond what the training data contains, but it's just hard to know exactly what is in the training data and what is not. So a lot of the power of these models is coming from the training data that they have. We have also said that these models hallucinate. If you talk with ChatGPT and you ask for things that might contain some factual information, then they will hallucinate the stuff. So you ask, where did I graduate from? It says, it's something, it looks nice, it's written in English, it looks beautiful. The first piece is true, but the second one is not true. It could have been true, but it wasn't, okay? So ChatGPT is not actually trying to tell you what is true. It's just trying to tell you something that could be. It's just sampling from those probabilities, saying, oh, this is a sequence of words that could be true because it has high probability. And this, it had high probability because I actually once was offered that possibility. So if there is some alternative world where this is true, and it's just ChatGPT doesn't know in which one it is. So, also, I wanted to tell you another thing is that these models look very surprising. A lot of the power is coming from the data. But there is another thing that is very important also, is that a lot of complex problems might not be as complex as they seem. For instance, let me do a quiz. You all know what a linear function is. A linear function is a function that if you take two inputs, the output is equal to the sum of the outputs if each input is processed individually. That's one condition. The second condition is that you take an input and you multiply it by a scalar. The function that applies to that scale input is equal to the output times the scalar. Okay, these are the conditions for a linear function. In fact, it means that, as Philip was showing before, a typical neural network layer is a linear layer, where it's just a set of weights, and the input and the output are related by the multiplication by a matrix. So in this particular case, this is the drawing that Philip was showing this morning. So I'm going to do a quiz. I'm going to show you a few transformations, and I want you to tell me which ones are linear and which ones are not. So here there are 4 transformations. The first one is taking a picture as input, and then you have to rotate it. The second one is a scaling of the image. The third one is to transform a color picture into a grayscale. And the final one is to defocus a picture. So think about it for 5 seconds. OK, raise your hands for all of you that think that number A, that A is a linear function. OK, let's say there is 15 people. B. No. B? OK. 30. C. Oh, OK. 10. 10 again, maybe. And D? OK. And how many people did not raise their hands at all because they just didn't care? OK, so there are a few. OK, good, good. It's just to calibrate the answer. OK, they are all linear. All of these functions are linear. You can find a linear implementation for all of those. If you take a rotation, if you take 2 images, you sum them and you rotate, it's the same thing that rotating them and then summing the rotated results. Or scaling is the same thing. You take 2 images, you sum them up, and then you do the scaling. It's the same thing that taking the images, scaling them, and then summing the result. The same thing for grayscale, and the same thing for blur. They can all be implemented with linear functions. What this means is that a linear layer in a neural network can do a lot of things. And sometimes a lot of the operations that we feel, oh, wow, what amazing is this thing that has happened here? Well, a linear function could have done it. It's not true always, of course. This is why neural networks have non-linearities and lots of layers. But linear layers can do a lot of stuff. And sometimes it's also hard to appreciate how strong can these models be, and the power from even simple models like linear functions. Okay, so now this is all the things that are going into the mix of what is happening nowadays in AI. On one side is some problems look complicated, but they are actually simple, and there are advances in a number of different directions that are all happening together. And in language models, this is a typical conversation that a language model and a human can have. Where in this case, let's say a human is a doctor and is sending some patient reports to the language model, and the language model that's been trained with data that knows a lot about medical diagnosis and so on is just outputting possible diagnoses, and there is a conversation. This is the typical conversation one can expect with ChatGPT. This is not exactly an agent. What an agent is when you start incorporating more stuff to it. So the first thing is that the human will not just provide information with language. It might actually provide information with different modalities. It could use images, voice, text. All of this is going to enrich the interaction with the language model. The second thing is that the language model itself, which is at the core of an agent, it also has coding capabilities, which means that it can take some of the instructions that the human is providing and translate those instructions into code that will get executed in order to use a set of tools. For instance, the agent could perform a search on a database. Maybe the database contains electronic health records, and the first thing that it realizes is that given a question, it requires actually to access the database, so it will write code that will access the database, it will get the results, and it will perform an operation. And then there are also planning tools that can be attached to this agent. One thing could be debates. It could be interaction with other agents, chain of thought, which is another tool for reasoning, and Philippe will be talking more about those things. Decomposing a task into sub-goals and then accomplishing each sub-goal independently, and so on and so on. So in that case, a conversation could go this way when you have an agent. The human sends to the agent some patient reports. The agent sends some possible diagnosis, but it doesn't send this diagnosis to the doctor. It sends the diagnosis to another agent that it will disagree or agree with those diagnoses, and it will say, in this case, okay, I disagree, request an X-ray. The first agent will interact with the human and will ask for an X-ray. The human gives the X-ray. The agent runs some code, accesses the database to get some health records from the patient to get more context, and then eventually provides a recommendation, and the human performs the final diagnosis. So this will be an interaction with an agent where now you have a system built around the LLM. So in general, an agent is going to be something that is a system, which could be an LLM at its core, that is going to perform actions in the real world. The real world in this case could be a database or so on. It could perform actions, and it will change its behavior based on the results of those actions. So for instance, when we were talking about that models hallucinate facts, like here when I was asking where I did graduate from, if you do the same thing in Bing, then what you have is that you actually get a slightly different behavior. If you ask the same question, the agent actually realizes that this question is better answered by first doing a web search. So it will perform the appropriate, it will write the appropriate code that will be hidden to you. You will not see the code, you will not see the execution, because there is a parser that parses all the time the outputs of the LLM, and whenever it sees code, the only thing that it does is run it. It doesn't show it on the screen. So in this case, it will perform a search on the database, and in fact, you can see that sometimes there is this message that appears searching. It's just executing that piece of code, and then it provides an output. And the output is a paraphrasing of the content that is on those web pages. That doesn't mean that the system will not hallucinate, but it's less likely because it's going to be using information that only needs to be paraphrased. So it doesn't have to create as much content as if it's just creating the answer by itself from the weights stored in the neural network. So it's less likely to hallucinate, but it's still possible. This does not prevent hallucinations 100%. But it can provide, for instance, links at the end that tell you what the sources are. So you click there, it opens the web pages that were used to generate this answer. But this particular text is not in those web pages as is. So it's been rewritten. So I wanted to show you just a couple of examples of agentic systems, just to go into a little bit more details of how they actually work and the type of things that you can do. So the first one is going to be ViperGPT, which is a vision system, and that was developed by researchers at Columbia University. And the second one is an agent for interpreting neural networks, which is something that we've done here at MIT. But the idea here is, these agents are going to be combining the power of language models with its coding abilities in order to solve tasks by also using tools that you have to provide them with. So let me talk first about ViperGPT. So this is a pretty interesting system that tries to answer questions about the content of images. And the basic idea consists of the following. You have a picture and you have a question that you want to have answered. And the system, what it's going to do, is going to write code that once it's executed, it will answer your question. And I'll explain now, I'll go into the details of how that works and what I mean by running code and answering questions. So here is an example of how a conversation with a vision-based agent can go when it doesn't have this, when you don't use this kind of agentic system, agentic structure with tools and so on. This is just off-the-shelf language model with vision that runs on the image. So if you ask, here in this picture, what are the boys eating? It just says the right answer, muffins. If you say, where are the muffins? It says on the table. So, here is getting things right. How many muffins are there? It says 2. How many kids are there? Too many. So eventually it gets confused, and you have these conversations that can derail very rapidly. So what they proposed was building an agent that will answer these questions. And the idea is the following one. So you have this image, you want to answer your queries, how many muffins can each kid have for it to be fair? So this is a sophisticated question that requires not just counting how many kids there are, but actually also accessing some common sense knowledge about what do you mean by being fair, and so on. So this is a sophisticated question that will require reasoning a lot about the question in order to find the answer. And the proposal is that then what you have is a system that will first write code so that if you execute this code, it will answer your question. So here is the piece of the code that was generated after that, and I'll explain later how that works. And what is interesting is that if you execute this code, so the first line will just find the muffins, will count them. You have a line that counts muffins. It says 8. Then you look for how many kids there are, the patches that contain kids. Then you count them. There are 2 patches. And then you compute the division of 8 divided by 2. That gives you 4. So the answer to this question is 4. So it's just a much interesting usage of how different tools that you can run on images will allow you to answer this question. So let me go in detail now on how all this works. So the first thing is this is not a system that is trained. This is just using a system that is already pre-trained, a language model that is already pre-trained that has coding capabilities like ChatGPT. And just as Jun was showing before, what you have is a prompt that will tell the agent, in this case, what kinds of functions it can use and how it has to call them. So there is a long prompt. So here is the beginning of the prompt. And the prompt is just the type of prompt, the description that you will provide, that you will write if you were writing a Python library, where you have lots of functions, and you have comments, and you have examples, and you put all this as text, and you just put it as part of your prompt. And then after this prompt, you attach the question that you have. So now, ChatGPT will understand that there are all these functions I can use in order to answer this question, and it will just write code to answer the question. So what is in this prompt? Well, there are all kinds of functions. For instance, there is going to be a function that is called find, that the input is a string with the name of an object that you care, and it will output an array of patches containing the objects that you care about. So it will return just small images, each one being a crop containing the object that you care about. So for instance, if you're finding muffins, the result will be these 8 patches. There are many other functions. For instance, anything that has been built by computer vision scientists. So here, there's another function that will compute the depth of the image. This means that it will tell for each pixel how far away is from the camera. So this is the picture. It just outputs a depth map indicating, in this case, it's a color-coded depth map indicating which things are nearby the camera and which things are far away. And there are lots and lots of functions of this kind. There are going to be functions that are application-specific, and these are the tools that you are providing the agent with. And then there is just the generic programming knowledge that the LLM has, that it knows how to write Python scripts, and then I can combine conditions, loops, and so on with the tools that you are provided to create programs that are relatively complex. So, and now you also have the benefit that you have all the common sense knowledge that the language model has. So when you ask for questions, the language model will use its source of its base of common sense knowledge to answer those questions. For instance, here, if the question is the animal that is not gray a dog? So that's a sophisticated question. This is actually quite difficult to answer for a language model directly on the image because negations get complicated. But here, the model just translates this image into code, and then it executes. So the first line finds the images with cats and dogs. Then it looks at one. Is this gray true? Is not gray not? Is this patch gray false? So this is not gray, so it returns yes. So here is the answer to that particular question. Here is another example, the computing math that is quite complicated. With the depreciation of this car, what will be worth in 5 years? So that requires understanding the make of the car, and then understanding what depreciation means, and so on, a lot of knowledge that the language model has. So it will just look at the code, it will write the code, and then it looks at the text of the car. It looks for what is the make of the car, so that gives you access to the depreciation rate. And then now it has also access to the current value, and just multiplies those two numbers, and it gets the depreciation. So it just gives you a number, which might be right or not, but it gives you a sense of the fact that this system can perform actually complicated queries. You can actually use it also on video. For instance, here there is a movie, and you want to know, return the 2 kids that are farthest from the woman right before she hugs the girl. So here is the hugging. Okay, so that's the question. And just using the prompt that I showed before, the output is this piece of code that if you execute it, it actually looks at, it parses the video into segments, and it starts looking for when a hug appears. So just executing each, looping over all the frames. Until it detects the hug. Keeps executing until it returns the 2 patches with the kids. So it's a pretty sophisticated reasoning. The systems are not, of course, it can fail in many different ways. There are many different types of failure modes that you can imagine. But this is a sophisticated question that requires like a interesting processing of the video, and it's through this combination of the power of the LLM, its reasoning capabilities, and all the tools that get added to it. So these systems have code available. This is the way that you build the systems is basically by engineering the prompt. Having the right prompt is actually relatively easy to get it working. It's difficult to get it working really well. So you really need to do things properly. It's very important that the library is written in a way that will look like as professionally written as possible, because that's how these things has been trained. It's trained by looking at code on the web. It's really good if things use a standardized language. Like if you start changing the rules of Python on the fly, it's just not going to perform very well. So you want to make sure that you respect as closely as possible all the conventions that are being used, and you write your functions in ways that are very, very familiar to what a programmer will be. And then it's just a set of API calls that you do with the language model. It could be an open source model or a closed model that has an API, and it's just a set of API calls. So that was for ViperGPT. And the next one is this multimodal interpretability agent that we've been working at MIT in my group. So here is a similar idea in the construction. So you have a language model that will be augmented with tools, and it will perform a question. You have a question, but in this particular case, instead of just giving the output once and you're done, you have a system that will, it will execute some code that will be based on the question that you have. It will run it on images. It will see results, and it will keep writing its code until it gives you the answer that you want. So it's like 1 degree more sophistication in how it actually interacts with the world outside. So what is that we are trying to do here? So one of the challenges when you build neural networks is that it's unclear what is that they are doing. Once you have trained it, you have all these weights and all these neurons, and yeah, the input and the output look good, but we have no idea of what is going on inside. How is that this output came about? Or when it's wrong, why is wrong? Can I predict what it will be wrong? So you want to really understand what are the different things that allow the system to work. So there are a lot of different directions of research that try to answer this question. And most of them are based on very specific ways of analyzing the content of a neural network. There are methods that are based on saliency, methods that are based on probing single units, and there are a collection of ways, each of those very specific on how they analyze a neural network, and they provide one type of answer. So what we want to do is once you have a neural network that is capable of performing some action, like for instance, maybe it's a discrimination where you have a picture and it classifies this image as being among 1,000 possible classes. So in this case, it says this is an airplane. But maybe I want to know what is that unit in the middle there doing. Okay, so I know what the output units are doing because they are giving me my outputs, but what is happening in the middle? I want to know what that unit marked in red is actually doing. So when you are trying to understand what a neural network is doing, there are many questions that you might want to ask. You might want to know what is unit 45 in layer 4 doing, or what are the biases in the output class for the dog class, or how many units inside the neural network actually detect cars, or so on and so on and so on. So you really want to have the flexibility for understanding the content of a neural network that is similar to the flexibility that you have to interact when you interact with a language model, where you can pose any question. So really what you would like to have is some agent that helps you understand what a neural network is doing, so that you can ask questions and this system will interact with the neural network and it will answer your questions. So that's what we try to do. What we try to do is to build an agent that is enhanced with a set of tools so that it can actually interact with a neural network that has already been trained to answer questions about the mechanism that the neural network has learned. So let me show you an example of once this system is built, how it works, and then I'll explain what are the different pieces that make it possible. So let's say that you have a user, you have this agent that will interpret that we call Maya, and at the bottom you have the neural network that you want to understand. So the user asks, what is the role of unit 122 in layer 4? And in this case, the neural network is a ResNet neural network, given with something that Kaimin discovered, and is trained to do ImageNet classification. So you want to know what that particular unit is doing. Why? Well, who cares? No. That's the unit that I had the sample for. So here is what Maya will do. So the first thing that it will do is will translate that question into a code that it will run in order to experiment on the neural network. And the first thing that it does, it runs a particular tool that what it does is takes the entire ImageNet, it passes ImageNet through the entire neural network, all of the images, and it records what are the images that most strongly activated that particular unit. So every unit will react to different inputs in different ways. And in general, if you have ReLUs, strong activations are considered to be meaningful. So if something activates very strongly that particular unit, then one could conclude that maybe that's the particular concept that is driving that unit. So here is the 3 images that most strongly activated that particular unit. The numbers, in this case, is just the activation score. And these units are convolutions, so they react to different pieces of the image. And the highlighted region is the region of the image that is responsible of that high activation. So Maya looks at these images. Maya is based on, in this case, on GPT-V. So it can take images as inputs, and it will analyze the output of those images. And it concludes that the highest activations seem to show bow ties. And indeed, if you look at these images, if you pay attention, you will see that all of them had a bow tie. So it seems to be firing near the neck. And these 3 images just by chance happen to have a bow tie. So now it wants to be sure that this is a bow tie detector. So it does the following thing. It calls a different tool that now it will generate an image. So this will not be an image that comes from ImageNet. Instead, it will be an image that is just generated. And it generates a face, and it sees that that does not drive the unit. The activation is very, very low. So now it says, well, now let's edit this picture and add a bow tie to it. And just by doing that change, suddenly the activation goes up again. And this image, the only difference with the previous one is that it contains a bow tie. All the rest of the pixels are more or less identical. This is another tool that I describe later that is capable of taking an instruction and changing the content of a picture. So now it concludes, well, this neuron seems to be selected for bow ties, particularly in the context of formal attire, because it performs more experiments. What I'm showing here is just a selection, just to give you a hint, some idea of what is actually, what it's going to do. So this is the full picture of the agent. You have a language model, a multimodal language model in the middle that can take as input text and images. And then you have a set of tools that it can call. The tools are going to be a set of functions that I'll describe in a second. And then it has functions to generate data, to send data to the neural network, and functions to read the behavior of the neural network. So for instance, one of the tools that it has is the capability of sending an image through the neural network and recording the activations and maps and activity maps of a particular unit. So you take a picture, you indicate a unit inside the neural network, and it outputs a number and a selected area. This is one tool. Another tool is going to be this dataset examplers, which is just, it takes a dataset of images, in this case, let's say ImageNet, again, a unit that you care about, and it outputs the top n images that most strongly activate that particular unit with their scores. So it's an array of tuples. You can have also image generative models. That's another tool. So in this case, it's Stable Diffusion, where you take as input text, and it outputs a picture that corresponds to that particular caption. So that allows the system to create images that might have properties that it wants to test, that might not be available on the original dataset that you provided with, because maybe you want to test something that is very fine-grained, and you really need to synthesize it. And finally, so there are tools to edit images where the input is one image. Then you have an instruction of what you want to do with that picture, and it outputs just that, the image with that transformation. Some other things might have changed on the picture, because this is a generative model that is doing the operation. But most of the changes are going to be the ones that you care about. But other things could happen. So this particular tool is based on instruct pics to pics, which is a model that allows to take a picture, an instruction, and transform it into another picture. This is another, I want to open a parenthesis here, because this is another very important aspect of modern generative models, is many times you have a model, you want to build something that solves a particular task, and we know that you need to have a lot of data to train these models. But in many cases, you don't have data. Like here, what we need is data that will, this is what we want to build. We want to build a neural network that will take these two inputs and output the transformed images. And you need to have data that has this form. There are triplets of an input image, an instruction for the change, and the output. And this is work that was done by Tim Brooks and Alyosha Efros and collaborators at Berkeley. So the challenge here is that you need to have a lot of data, and this data is not available out there. So one of the things that is happening now in the field is to use all the different tools that we have nowadays built, language models, generative models of different kinds, and so on, in order to generate synthetic data that you can use to train new models. So for instance, here, this model was trained using synthetic data. So the way that the synthetic data is generated is quite creative, and I think that a lot of the research now comes into how do you figure out ways of generating synthetic data that has the conditions that you care about. So here is what the process was. So the creation of the training data started by just asking GPT to start with a caption of an image and propose a sentence that will be an instruction for an edit, and then another sentence that will be the final description of the image after that edit. So you don't need, this is something that you have. You can take ChatGPT and you can ask it to do this, and it will create these triplets where, in this case, you say photograph of a girl riding a horse, and then the instruction can be have her ride a dragon, and then the output should be a photograph of a girl riding a dragon. So you give 1 or 2 examples of what you want, ChatGPT can just generate more of those. The only thing that you need to start with then is a collection of image captions. And there are lots of databases out there that contains a lot of image captions that you can use to then ask ChatGPT to create triplets of this kind. So this is one piece of what you need. The second thing that you need now is to generate also pairs of images of before and after. And in particular, there is a particular approach that is called prompt-to-prompt that allows you to do that. So if you have 2 prompts, each one with a slight variation of the other one, they can generate 2 images where the only change is whatever changes between the 2 prompts. But once you have that, that's it, you're done. Now you have, now you have pairs of images and the instruction. You just need to reorder the order in which inputs and outputs are defined, and that's it, you train your model. So that's a very creative way of creating your training data. It's fully synthetic. There are no real examples in this training data. So this is, once you have defined all these tools, this is how the Maya prompt will look like, where you have, it's again a bunch of code that will look like a Python library that is just part of what you input in the text command. And then you ask, OK, now tell me what unit X is doing in this neural network. And it will just use the code to write the script that is necessary to understand what the neural network is doing. What is interesting is that it actually will not just run the code and give you a straight answer right away. It will actually keep refining, creating hypotheses and running experiments until it reaches a particular answer. So it will not stop by just running the code once. So here is what happens in one interaction with Maya. So you start saying, OK, what is that particular red unit there doing in a particular pre-trained model? So the first thing that it does, it runs this code that throws all the entire ImageNet through the neural network to see what most strongly activates that unit. And we don't tell the agent to actually start experiments this way. It decides by itself that that's an interesting way of starting because it will narrow down the number of hypotheses. So here there are, it returns 5 images, and they are the 5 that it returns. So you can see the activations in this case goes from 0 to 1. So these are strong activations, and it's highlighting this spherical object. But in fact, Maya looks at the images, and it concludes that, that these images seem to be showing spherical objects interacting with hands, which if you pay attention to the images, you will see that there is a hand always over there, not in the selected area, but just nearby. So then it says, well, let's actually check if this is true. So let's perform some editing experiments to test this hypothesis. So it runs the following experiment. It uses 2 prompts to create 2 images, a person holding a banana and a person holding a cube. So these are the 2 images that it generates that are not spherical objects. It's a hand interacting with an object, but not a spherical object. And now it runs this through the neural network. It has to write code to do that too. And these are the returns, very low activations. The unit doesn't seem to care about these images. And now it says, well, now let's edit this image from non-spherical to spherical. And let's analyze again the neuron activation. So it runs the tool that transforms images with an instruction. In this case, these are the 2 commands that it sends: replace the cube with a red ball, or replace the banana with a ball. So just to remind you, these are the 2 input images. And after these transformations, the first one becomes a hand holding a ball. You can see that the hand is not perfect. This, These models are not perfect, so there will be a lot of issues there. And then the banana gets transformed into this, which is pretty interesting, no? To see that this is a pretty cute transformation. So it runs these images through the neural network, and it sees that now the neural network gets activated with these images. And in fact, if you compare it with the previous activations, you can see that there is a big jump in the activation. So it concludes that, yeah, indeed, this neuron seems to be selective for hands interacting with physical objects. And now you can say thank you, and because it's an LLM, it will tell you are welcome. And just to remind you that at the end, you're interacting with an LLM, and things can get offhand quickly, depending on what you talk about. So we know this is correct because we actually synthesize this unit. This is not a real unit inside a neural network. This is something that we have created synthetically so that we can evaluate performances. In this case, we are using SAM, which is a segmentation algorithm that is driven by text, and we use that to create a model that will actually be selective for balls when hands are interacting with them. So this output was generated by this model that we created. So we knew exactly what the ground truth was. So we used that in order to evaluate the model. We had lots and lots of different units that are fake, are not real units, that we used to evaluate this model. But we find similar behaviors on real units. So here is another one. This is a real unit inside a neural network. This one is selective for tennis balls. So it runs all these experiments. It formulates a number of hypotheses. So it's behaving like a scientist. And it's running, it's creating prompts that will test each single hypothesis. Then it runs all this on the neural network. It sees, it's testing different contexts, whether the ball, it can be any ball, like if it's a soccer ball, does it work? Or if it's a yellow field, like maybe it's just the color that is selective for, and it concludes that, no, this seems to be really selective for tennis balls. So at the end, it performs a number of experiments until it reaches that conclusion. It's actually quite creative. These models can get quite creative in the experiments they run. So here is an example where it's run a series of experiments, and it found a neuron that is selective for facial features on animals, particularly selective for eyes and noses. So then it decides to create a picture that will contain a cat's face with clear eyes and nose, and it runs this through the neural network. Here is the image, and here is the activation. So effectively, it seems to be reactive to the nose, and I'll leave it to the eyes, and it gives some score. And now it says, well, let's transfer the cat's eyes and nose onto coffee cups. This is very creative. Like, this is a very creative experiment. And you run the edit tool, and it gives you this picture, which is very interesting. And it runs this, and it does not activate the unit. So this is an example of how creative this can get. This is another example where it's realized that some unit seems to be selective for birds, and it's focusing on the heads. So it creates 2 images of birds sitting on a branch, and you see the ×2, just using like Python tricks in order to do these things. It creates these 2 images, and now it says, well, let's replace the head of the bird with a cat head, and the head of the bird on the second image with a dog head, which is crazy. And then here are the original images. These are the transformed images, and let me zoom in. These are the heads that they put there, so it really does look like a cat and a dog. And yeah, the activations just go down quite substantially. So it just concludes these experiments and continues doing. And then, of course, it has failures. For instance, here, it concludes that there is some unit after some experiments that seems to be reacted to faces. So it creates an image with a family picture. The unit seems to actually not care about faces, but that doesn't seem to bother the model. And it says, well, let's flip the family picture upside down just to test if this is really selective. And flipping an image upside down is a very simple task. You can actually write in Python the code that will do this. It's very simple. But instead of that, it uses the tool to transform an image, which is just the wrong tool to use. And it gives this output, which is crazy. And it just, it says that it does not activate the unit. And still it concludes that, yeah, this is selective for parts of people and so on. Like, this is an example of a failure of reasoning. Like, the tools did not work. the images are not supporting the evidence, and the model still just happily goes and says whatever it wants to. So there is some confirmation bias going on here. So with this, I will conclude. So you can see agents are just this way of creating tools that solve tasks. So an agent is really an LLM at its core in general, enhanced with tools so that it can interact with a world outside, perform actions, get outputs, and change its behavior based on those outputs. So with that, I will conclude. I can take a couple of questions while Philippe comes to the podium. Thank you. So the question is, what are the most promising uses? What do I think are the most promising uses of agents? Well, I think that agents are, there are lots of promising uses. I think that anything that has to do with tool use. So I think that, for instance, they are very exciting in the education domain, where you can actually have agents helping teach material, where they will ask questions to a student, get the results, and refine the type of interactions that you want to have so that the student actually learns some concepts. So that's a very interesting area of research. Of course, in healthcare, there are lots of potential uses, and people are already using them in different ways. There are lots of challenges also with the use. So there has to be a study of their failure modes and how to better use them and so on. But these are like some examples of interesting areas. But I think that in scientific discovery, they are going to be very exciting. So let me take some more questions over there. So the question is, some of these experiments, as is performing experiments, they seem a bit random, and is there any guidance on how it should perform the experiments so that it's not so random? In this particular set of experiments, we did not provide any guidance besides what appears on the library with examples, but there are no examples of how to actually, we don't guide it on which order, on what type of experiments it should be running first, but that's something that you can do. You can incorporate into the library a description of what are common uses and in particular scenarios, how it should be used to answer particular questions that are predefined. If the question goes outside of that, then it's left to its own devices to figure out some other random process. But if you have a set of interactions that are very commonly going to happen, you could provide guidance on how to do that, just like in the same way that as humans, we know exactly which steps to follow when we solve tasks for which we know there is a procedure that normally works. So here you can think of something similar as how you will train humans to solve tasks. So we'll have more time for questions after, but